but you can have a similar window periodic sequence for downsampling by any other factor. So, suppose you were to downsample by m in general. Again, let us take the example now of a variety of m equal to 4 this time. Then the corresponding PWN would be 1 located at 0, then 3 zeros, 1 located at 4, then 3 zeros again, 1 located at 8 and so on this side, and of course, 3 zeros and then a 1 and so on this side, periodically continued. Continued this way, continued this way. So, what we are saying in effect is the process of killing, the killing process is essentially multiplication by PWN for the appropriate m. So, if you want to downsample by 2, you have an appropriate PWN, periodic with a period of 2, with ones located at all multiples of 2 and zeros elsewhere. In general, when you want to downsample by m, you have a periodic sequence PWN with a period of capital M, ones located at all multiples of capital M and zeros everywhere else. Simple enough. What about the compression step? The compression step can be viewed as an inverse expander, an inverse upsampling step. So, maybe we should say downsampling by m means, or in other words, let us actually put down sequences here. Let us say x n has been downsampled to produce x d n, and that means x n has first been multiplied by PWN. PWN for downsampling by m, for m in brief. And then now look here. You know what we are saying is x d n is here, and I am saying upsample by m, but this way. That means it is a reverse or it is an inverse upsampling operation. Now, if we view the downsampling operation this way, it is again very clear why it is not invertible. This part is invertible, but this part is not, because you cannot divide by PWN. PWN has zeros in it, you can't divide by them. That is another way of viewing it. And of course, this will also get manifested in the Z domain, but subtly. Now, you know, to manifest this in the Z domain, this operation of multiplication by a sequence is difficult to capture in the Z domain. So, what we need to do is to translate this multiplication by PWN into multiplication by other sequences which are easy to interpret in the Z domain. Now, the only convenient multiplication by sequence operation which can be handled in the Z domain is multiplication by an exponential. So, what we need to do is to replace this multiplication by PWN by a linear combination of multiplications by exponentials. How do we do that? So, let me put down our objective a little more clearly. this multiplication by PWN needs to be replaced by xn multiplied by exponential alpha 1 to the power of n. So, I think maybe I will say multiply by alpha 1 to the power n plus say alpha q to the power n, q such terms. Same xn. So, multiplication by alpha 1 to the power of n or alpha to the power of n in general is easy to handle in the z domain. So, the other way of saying it is we need to express PWN as a linear combination, let us say Ck times alpha k to the power n, k going from let us say 1 to q. Now, this is not at all difficult to do. In fact, if you think about it, that is exactly what the discrete Fourier transform does in discrete time signal processing. The discrete Fourier transform essentially expresses a sequence, in fact, a periodic, a time limited sequence as a combination of exponentials. Let me just, to refresh our ideas, put the expression for the inverse discrete Fourier transform before us. So, if you recall, if you have a time limited sequence, let us say it has capital N samples. So, you have, let us give the sequence a name B 0 to B n, or B n minus 1 to be more precise. So, if this is the time limited sequence of capital N samples, its discrete Fourier transform, if you recall, is essentially capital B of k. Of course, k also running from 0 to capital N minus 1, with capital B of k defined by summation n going from 0 to capital N minus 1 B n e raised to the power minus j 2 pi by n capital N times n k. And then we can reconstruct B n from its discrete Fourier transform. That is easy. B n is 1 by n, summation k going from 0 to n minus 1, capital B of k e raised to the power j 2 pi by n k n. Now, this is true for again n going from 0 to capital N minus 1. But after all, if you recall, what we have here in the discrete Fourier transform expression and in this expression, which is essentially an inverse discrete Fourier transform. Recall that the discrete Fourier transform is often abbreviated by DFT and the inverse discrete Fourier transform by IDFT. In the IDFT, we have exactly the kind of expansion or expression that we desire. We are expressing that limited sequence of capital N samples in terms of its DFT components and exponentials here. So, we have exactly what we want. Now, we can exploit this. You see, what is to be noted here is that although we have talked about a limited sequence, actually you can periodically extend that sequence in capital N, and whatever expression we have here to reconstruct B n from capital B of k. So, B n is reconstructed from capital B of k here, seemingly only at n equal to 0 to capital N minus 1, but even if you apply the same expression for all integer n, you get a periodically repeated sequence. Whatever is between 0 and n minus 1 is periodically repeated in every interval of n successively and before. And that is easily seen if you substitute n by n plus any multiple of capital N here, noting that e raised to the power j 2 pi by n times capital N is 1. Let me do that just for completeness. So, what I am saying is, if we use this expression, the expression summation k going from 0 to capital N minus 1, capital B of k e raised to the power j 2 pi by n k n generates a periodic sequence. So, let us call this expression as a function of n b tilde n. It is very clear that b tilde n plus L times capital N is essentially summation k going from 0 to capital N minus 1 b k e raised to the power j 2 pi by capital N k n plus L times capital N, and this can be simplified. We have k going from 0 to capital N minus 1 b k e raised to the power j 2 pi by capital N k n times e raised to the power j 2 pi L, and this is essentially 1. So, this is essentially 1. So, you may remove this term and leave this, and that is the same as b tilde n. And therefore, what we are saying is, in effect, b tilde n plus L times capital N is b tilde n for all n, and therefore, periodic with period capital N. So, here we have a mechanism for generating a periodic sequence by using a combination of exponentials. Let us exploit that. So, let us now take the case of capital M equal to 2. There it is easy. We need the periodic sequence well 1 0 1 0 and so on and so forth, and we exploit just one period here. And we construct the discrete Fourier transform of this. that is easy. It is 1 times e raised to the power minus j 2 pi by 2 times, of course, the discrete Fourier transform is a function of the frequency index k. So, this is 0 times k plus 0. So, in fact, b of k is 1. For k equal to 0 and 1. And how do we reconstruct this sequence, the periodic sequence P w n then for m equal to 2 is reconstructed using the inverse discrete Fourier transform. So, it is summation k going from 0 to 1 b k e raised to the power j 2 pi by 2 times k n, and that is easy to do. That is half summation k going from 0 to 1 times e raised to the power j 2 pi by 2 is j pi k n. So, in fact, let us expand it explicitly. So, that is half. With k equal to 0, it is 1 raised to the power of n plus minus 1 raised to the power of n. And now, we are well set. In fact, we are almost there. Indeed, what we are saying is, if you have x n and if you are multiplying this by this sequence and you wish to obtain the z transform here, all that you need to do is to say express the following expression n going from minus to plus infinity x n into half 1 raised to the power of n plus minus 1 raised to the power of n times z raised to the power of minus n in the z domain, which is easily seen to be summation n going from minus to plus infinity. Of course, half can be brought out everywhere, x n z raised to the power of n plus half summation over all n from minus to plus infinity x n minus z raised to the power minus n. So, we have done our job. Indeed, these are very familiar expressions. This is just the z transform of x and this is the z transform of x with z replaced by minus z. So, we have this is essentially equal to capital X evaluated at z plus capital X evaluated at minus z multiplied by half. So, we have done our job. Now, all that we need to do is to note that this goes through an inverse upsampler by 2, so to speak. And therefore, if we put these together, we have the final result x n with z transform capital X of z, when it goes through a downsampling by 2 becomes in the z domain x d n with the corresponding z transform given by half x z raised to the half plus x minus z raised to the half. We have done what we wanted to in this lecture. We have established the z transforms of the basic multirate operations in terms of the original z transforms of the sequences. We shall build on this further in the next lecture to carry out the complete analysis of the 2-channel filter bank. With that, then, we conclude this lecture and look forward to the complete analysis. Thank you.